Okay, so you all know YouTube, streaming video site, been around for a while, briefly as an independent entity, almost immediately acquired by Google, and its main revenue stream is advertising. There's also some other things, there's paywalls, right, things that you have to pay for, like if you want to see a recent movie, you might be able to watch it on YouTube for like $3, or subscriptions, right? So every now and then YouTube throws out a subscription plan so you can sign up and not see ads. The last one of those was YouTube Red, not to be confused with RedTube, right? So anyway, Scale is a very, if you don't know what RedTube is, that's okay. Scale, number 3 website in terms of visits, so it's very busy. It's one of the big players. About 5 billion video views per day, and a big chunk of them through mobile devices. Don't know exactly how many videos are up there. I haven't seen terribly recent stats on this. But last I checked, few billion, think of the range like 3 to 5 billion videos up there, and probably a couple million getting uploaded every week. So there's a lot of data they got to manage. Okay, so it's a big operation. Now, quality of service, which is what this lecture is all about. Quality of service is a term that's applied to network systems and applications. And basically it means how well it's working, right? Especially in regard to data transmission rates, how much data you're getting, how quickly, and reliability. Are the messages actually getting to where they need to go, okay? Now, as we'll talk about in a little bit, there's a lot of case-specific details that, for example, there's different reasons why data transmission rates can start to falter, and depending on the application, it may be more consequential when they do. So because of those kind of case-specific details, quality of service is just kind of this buzzword that people understand. We have really good quality of service. Yeah, okay, that means everything's working fine, okay? But it doesn't mean much beyond that. So, give an example. If you send an email out to somebody, you probably don't care very much if it takes 10 seconds or 30 seconds or even a minute to get there, right? Email is not typically one of those things that demands instantaneous response. On the other hand, if you're playing some kind of, live action video game online with like 10 of your buddies, everything you do, you want to be super fast, right? So, what might be a perfectly fine quality of service for an email application might be intolerably slow for online gaming, right? So that's what I mean when I say case-specific details. What's enough quality of service for one thing might not be enough for another. Anyway, so other examples. Typical users would probably have the following preferences, right? So, you're sending out an email, you're very concerned that it gets there, right? Because otherwise, why are you sending it? But if it takes a little while, yeah, okay, you can live with that, right? So if you got to pick one or the other, you're going to pick reliability over speed. Likewise, if you're uploading single images, say to Facebook, right? You went on vacation, you got a stack of photos, you upload them. You probably are really concerned with the image quality, right? That everything looks exactly the way it did when you upload it, and there's no errors in transmission, so there's like little fireflies floating around in the images. And you're less concerned with speed. If it takes a little while for them to do it, well, so be it, right? You don't want to risk having your beautiful vacation images look like garbage. Last, video. Now, video is different, right? Especially streaming video. Basically, most users are really concerned with the flow of the video. So, typical humans can only process about 24 frames per second. Goes any faster than that, and humans don't really see it. It goes from looking smooth to still looking really smooth. So, if you lose a little bit of detail in there, right, you're planning to play something at like 30 frames a second and you lose a whole frame, typical human might not even notice, right? So in that sense, speed and reliability, right, but in particular speed, keeping the data flowing and keeping it flowing continuously is probably more important than occasional minor data loss. Okay, it's like if you're listening to the radio in your car, for example, and there's like one brief second where there's a little glitch in the noise, yeah, it's kind of annoying, but imagine it would be so much worse if you like got 10 seconds of music and then it stopped for 5 seconds, then you got 10 seconds more, then it stopped for 3 seconds. You'd be like, oh fuck, turn the radio off, right? It's more important to keep the flow going. Okay. Now, streaming video. So if you had very high quality of service, in a streaming video context, that would basically mean you could watch the video from online just about as fast as if you actually had the video stored on your machine locally and you were watching it from there. Okay, so data stream, we'll talk about data stream because this is something that comes up with YouTube. A data stream is just a set of transmissions with a specified order. So every video essentially gets broken up, right? So if you have a video, what is a video? Well, number one, two streams, right? Video, which is just the pictures, and audio, which is the sound, synchronized. Then, for transmission, video broken into frames, frames broken into packets. Right? Packets are the basic unit of network data transmission. So think of packets as basically being mini emails. Okay, typical packet size maxes out at about 1.5 kilobytes. Okay, so that's what happens. You have a video that, 2 hours of video at, say, 24 frames per second is going to get translated into what's two hours, did I say? 2 hours is 7,200 seconds, so 7,200 times 24 is what, 144, and then so something like that. A lot of data. Anyway, a lot of frames. Each one of those frames, right, if it's a full square of an image, that's probably several kilobytes at least. And so that's going to get broken up into like 10 or 100 packets, depending on how fine resolution it is. Okay, and all those have to get sent in sequence. Okay, all packets sent in sequence and assembled to make a frame. All frames shown sequentially to create the video effect. Okay, that's what videos are. Okay. Now, so each transmission, right, is going to be some portion of the video, and the entire set of transmissions is going to mean the entire video. Once you've gotten all the transmissions, so all the packets composing all the frames, then you can view the complete video. But what are some problems? So 20 years ago, if you wanted to view a video from online, basically that meant you went to some site where you found it, and a typical music video might be about 3 megs of data, which on our shitty dial-up connections back then took like 20 or 30 minutes to actually download. It pretty much sucked. So you do that, you download the whole video, which took a really long time, but once you did, then you could play it as many times as you want. So, but what are some problems? Well, for example, number one, what if the frames arrive out of order? Imagine if you got the first frame arrives last. Well, guess what? You can't start playing the video till you get that first frame. Second, if you're waiting for the entire video, that could take a really long time, right? Even these days with fast connections, if the video is a couple gigs, like a a DVD quality movie, full-length movie could be, that could take a little while to download, right? It could take a few minutes. Could take several minutes even if it's that much. And you probably don't want to wait that long to start watching. Last, what if a few frames arrive very late or never, right? You have this huge sequence of data, but one piece of it never shows up. The packet gets lost in transmission. You don't find that out until the whole download sequence is done. You got to do it all over again. And again, this was something that happened fairly often 20 years ago. You download the whole video. You'd find that something went wrong during transmission. It didn't play. It said video is corrupted, cannot play, blah, blah, blah. Got to download it again and hope is just a fluke and not the actual video itself. Okay? So these are some typical problems. Now to address this, what YouTube typically does is it loads the videos in segments. It'll load the first chunk and then subsequent chunks as it needs them. So we'll go, now is where we actually go to YouTube. We'll watch Coraline Button Eyes. So watch very closely when I start watching this. You'll see instantly, blurp, well, we'll see that. We'll get through, yeah, this is the same ad we had in the morning. Hooray, Barbie Dreamhouse. All right. Why not buy 6? Okay. Boom. So, oh, it kept me because my account. That's kind of wacky. I wasn't using this machine, but I was using a different account, and it retained where I was. But you'll notice, right when it starts, it saves a chunk of data. You see that heavy gray bar there? That's how much of the video data it already has. Video doesn't start playing until it downloads that chunk. Okay, and then as I watch a little more, it starts creeping along to keep ahead of me. But the idea here, a lot of times when people go to YouTube, they'll basically do channel surfing. You all know what channel surfing is? What's channel surfing? Yeah, you watch a little bit, say, oh, this sucks, flip to the next one. Oh, this sucks, flip to the next one. Bup, 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 bup. People do that on YouTube too. Well, guess what? YouTube doesn't want to spend all of its network time and capacity downloading videos, complete videos to people if they're only going to watch a few seconds. So until YouTube is pretty confident that you're going to stick around and watch the whole thing, they're not going to bother trying to download the whole thing to you. Okay? So that's that. Let's get back to the slides. So, typical quality of service problems. What kind of problems are common for streaming video? Well, number one, slow starts. That first chunk of data could take a while to get there, right? If you got a crappy connection for some reason, right? You move so that there's a big wall or a couple walls between you and the wireless access point, and suddenly you can't get a great signal. Yeah, it could take a while to get that first chunk of data. Second, choppy video, right? If it starts and stops a lot during play. You get a little bit of data, it plays for like 10 seconds, then it stops. Then a while later you get a little more, and that's annoying and you don't want to watch a video like that. Last, bad quality, right? So if something goes wrong that you're not getting all the detail for the video, I mean, if you lose a pixel here or a portion of a frame there, it's not that big of a deal. But if you're losing a lot, right, and it starts looking like that kind of fucked up TV static kind of look to it, then yeah, I mean, that's why are you even watching that? So, generally speaking, all these issues have the same root cause. Too much traffic on the network. So, all the cables going from the network to you, right, going from, say, YouTube to you, are basically like roads for data. And what happens if you have too many cars on a road? What happens? You get congestion. And what is the practical consequence of congestion? Cars start moving slow, right? Same thing with data. So, if you're on a real road, if there's, say it's a big 4-lane highway, you can have 4 cars zoop going on in parallel basically at full speed. If there's reasonable spacing between the cars, you can have a whole sequence of cars going at basically full speed. But once it starts to get, more congested, you have cars wanting to make lane changes, other cars wanting to get off at exits, new cars coming in, they got to make room for them. Everything starts to bunch up and slow down. Same kind of thing with the network. When you try to put too much data through the cables, basically it stops going very fast. In the technical term, just like traffic congestion, you have network congestion. It's basically the same problem. So, conceptually, way to think about it, number of users times the number of apps they're trying to do at once times the amount of data each app requires. So basically, if you add more users, if you double the number of users, you're going to double the amount of traffic. If you double the number of apps, you're probably going to about double the number of traffic. All these things are multiplicative. Now, when network traffic exceeds the system's effective capacity at any point, delays are going to happen. So, we're going to draw a very simple, very simple network diagram for our example. Okay, so we have a few things here. Now I'm going to make the font a little smaller than I had it because, okay. Do 16. Okay. So you guys know what a switch is? What's a switch? Well, not in this sense. What's a network switch?
Does it switch the amount of internet going to certain devices?
Kind of. Yeah, it's basically a big box with ports that handles traffic. Okay, so basically traffic can go in through one port, all those old, things that look like phone jack connections, they go in on one port and goes out on another port. That's what a switch is. So it arranges, if there are a bunch of different devices connected to it, they can all exchange data that way. Okay. So over here on the left, we have source 1. Over here we have source 2. And on the right, we have user 1 and then user 2. Okay? And let's assume all cables have 1 gigabit per second capacity. That's how much data they can send, 1 gigabit per second. Okay? We'll keep the example simple. Now, if user 1 is sending data this way, right, user 1's getting data from source 1, user 2 is getting data, from source 2, they can basically operate in parallel and they'll pretty much get close to that 1 gigabit per second. Okay? Because everything from source 1 is staying on this pair of cables, everything on source 2 staying on this pair of cables, right? And we're going to assume the switch is fast enough that it doesn't really mess up the process. Okay, everybody can agree with that? Simple network diagram? Make sense? Okay, good. So what happens? Network traffic exceeds the system's effective capacity. What happens though? All of a sudden, user 2 also wants to get stuff from source 1. Well, if user 1 plus user 2 is less than 1 gigabit per second, roughly, no problem. They get their data. But if user 1 plus user 2 is greater than 1 gigabit per second, somebody's got to wait. And depending on what prioritization scheme you have, if you say user 1, right, gets first priority, maybe user 1 gets all of their traffic and user 2 gets some or none. Or the other way, maybe user 2 has priority, or maybe they're going to have to share. Maybe they're considered equal and they both get about half that, because all that can come down this cable here is 1 gigabit per second. And if that splits off at the switch, then they can only each get about half a gigabit per second. And this is fundamentally why when you go to some online game that's brand new and popular and everybody wants to connect to a particular server, this is why shit slows down, okay? Because everybody's trying to get all that same data through one piece of cable. And there's only so much capacity it has to be split out over all the users. Okay, so more users, each one gets a smaller share of the data rate. Okay? Does that all make sense so far? Questions? Yeah? No?
So that's one cable.
Yeah, all these black lines are cables. Yeah, basically, there's going to be a series of packets coming down. Some of the green ones go to this guy, some of the blue ones go to that guy, but I can still only send out so many of those packets per second, right? If it were just one user, I could get the full 1 gigabit, but if there's 2 users, they got to share it somehow. Yeah. Okay. So, moving on. Another example. Suppose you have 2 transmitters A and B that also want to transmit to a receiver R. So we're going to temporarily get rid of this, then we'll come back to it in a minute. So suppose I have these 2 guys, A, B, and R. Okay? And this works well if you're thinking like mobile devices communicating with each other. So, suppose it's like a crowded room, and there are 3 people there, and they're kind of all in each other's faces. If one of them's talking, right, if just A is sending to R, R can understand. If just B is sending to R, R can understand. But if A and B are talking at the same time, R is going to be like, what? Too many words, can't get it. Okay? And at a signaling level, what happens is something like this. So, if this is A signal stream up here, damn it, why isn't that click taken? Okay, this is A, this is B. And suppose A is sending out signals that, look like this, and B is sending out signals, I don't know, let's do it in blue, look like this. Okay, what's going to happen when these 2 get received at the same time is this, essentially. It's all going to be gummed up. The top is what R is going to get. It's not going to get either signal correctly. It may not even be able to distinguish whether A or B is sending. It may, even that information in the message, the fact that one message is from A and another is from B, even that might be garbled. So, when these 2 devices, when A and B are both trying to transmit to R at the same time, the signals can, interfere with each other, can mess everything up. Okay. So, now if your network is low utilization, that is to say it's not very busy, which is often the case. If you have some network of remote devices far away from power sources, you just put them there as kind of a monitoring system. Okay, that's sort of unregulated transmission. That might be okay, right? If the network is not very busy, then you might just say, well, we know the devices, they're not transmitting very often. It's pretty unlikely that they'll interfere with each other. There aren't that many devices in the first place. It's not that big of a deal. But as the network gets busier, right, if you go from having, say, 3 people in a room to having 1,000 people in a room, and anytime more than 2 of those 1,000 people are involved in a conversation, nobody else can hear, what happens? Well, number one, interference happens a lot, right? More devices, they're going to try to transmit more often. The case of 2 devices transmitting at the same time is going to be really common. Second, a lot of these transmission protocols, they have retransmission attempts. Basically, if a transmission doesn't go through, they're going to try it again. But guess what? If your network is already too busy to handle the traffic, and then on top of that, you start transmitting every time a transmission fails, that's just going to make it worse, right? Then the whole network is just going to be flooded with these retransmission attempts, and nothing's going to get through. So what will eventually happen, traffic will get backlogged, often never delivered. What will happen is that connections will time out. Every device tries and tries and tries to send out these transmissions. They get blocked or interfered with so many times, either one, the system gives up, says, well, I tried to retransmit it 5 times, I'm done, or the connection times out because they haven't been able to, exchange data with anybody in the preceding 5 or 30 seconds. So, in practice then, what you do, you need some kind of mechanism for all these devices to take turns, right? If we go back to our slide here, basically you want some kind of system where A and B both know they're in the network, so A says, all right, I'm going to transmit some of the time, B, you're going to transmit some of the time, we'll try not to step on each other's toes. Okay? That's what you want conceptually. Okay. So, transmission scheduling, right? That's when we talk about transmission scheduling, that's all we mean is devices taking turns transmitting. So, basic ideas are this. Number one, transmitters shouldn't transmit if another device is transmitting to the same receiver. So, if A is transmitting, then B shouldn't try to. If B is transmitting, then A shouldn't try to. If it does happen that 2 devices do transmit to the same receiver, they're going to wait and they're going to have a random delay before they try to transmit again. What would be wrong is if you did why would it be a problem to not have a random delay? What would be the problem? A and B both try to transmit. They wait exactly 1 second before transmitting again. What happens? Yes, that would be live lock. Excellent. Okay, so basically, if they both retransmit at the same interval, well, if there was a transmission interference before, if there's a collision before, there's going to be a collision again when they both try to retransmit exactly 1 second later, which, yeah, is a kind of live lock, right? The system is trying to respond to the blocked state, but the way it's responding with an exact, same time, it's going to perpetuate the locked state. So, last thing, repeated random delays tend to be longer. The idea there is if there are more devices in the network, every device is going to have to wait longer between transmissions. Okay, so if a device has to wait over and over and over, the implication is that there's a lot of other devices also transmitting in the network. So the network is going to adapt to being busier that way. So every time a device finds it can't transmit, it's going to wait a longer time. And that way, the approximate interval between transmissions will get pretty close to, a fair amount where everybody takes turns. Now, this isn't a computer engineering course, computer science course, so we're not going to go super in detail into transmission schemes, but just, be aware, there's a lot of different ones out there, different optimizations. For example, you might try to minimize average delays, which means you try to send as much data as possible through the network. Or you might try to minimize the risk of interference. You might try to ensure that devices are pretty careful about transmitting when anybody else is because they don't want to conflict with each other. Or you might have the idea that you want to ensure equal participation, that basically every device in the network gets an equal share of the network's capacity. And generally speaking, you can get one of those, but you can optimize one, but by giving up something on the other two. So, anyway, excuse me. So just 2 more slides, then we'll call it a day. So, the 3 big video problems, network transmission problems generally, latency, jitter, and packet loss. Okay, so everybody knows what latency is, I hope. You've experienced it. When the network is slow, right, everything that you're trying to do takes longer. That's what it is. It's just a transmission delay. And it can happen at the source of the data, or it can happen somewhere on the path to getting the data to you. Now, all transmissions have some latency, and the typical number is about 1 millisecond for every 100 miles. And that's just because electrons don't teleport down those cables. So if you have a communication with something on the other side of the world, right, there's some server hosting something that you're doing, your delay is probably going to be about 1/10 of a second, about 10,000 miles, and that's how long you're going to wait. And that's in addition to any system processing going on. Okay? And if the network is busy, if it's congested, there's obviously going to be additional latency as well. Now, jitter is variability in latency, variability in the delay of transmissions. And this happens essentially, some transmissions are really slow, some transmissions are not. Okay, now just like latency, some jitter is always inevitable, right? It's not a perfectly regulated system. There's always going to be a little bit of variability in latency from one packet to the next. It just might not be big enough for you to notice. I mean, if it's on the order of nanoseconds, yeah, it's still there, but you're not going to notice it. But jitter can become severe primarily when congestion affects a subset of transmissions. Okay, so let's talk about these for a second. Okay, so we're going to go back from here to here we go. Okay, so again, we're going to say 1 gigabit per second for all of these cables. We have user 1 getting data from source 1, user 2, blah, blah, blah. Okay, let's make a new supposition here. So, we're going to say both user 1 and 2 are pulling data from source 1. Okay? And assume that both request 1 gigabit per second from source 1. So what do we know? We know that this pipe, this cable here, can only transfer 1 gigabit per second. We know that these guys, right, together, they're requesting 2 gigabits per second, right? There's not enough network capacity to do this. So they wait. That's latency, right? Everything you're trying to do is going to take longer, okay? Because again, in this case, because they're sharing the network capacity. So what might under normal circumstances take a second to do might take 2 seconds, right? If there are a lot of other users, might take much more. It's one of the things with latency. Okay. Another possibility, imagine that user 1 has absolute priority for this application data. Okay? That means anytime user 1 shows up, user 1 gets whatever. User 1 gets as much data as a request up to the cable transmission limit. Okay, so, you know, he's not going to get more than 1 gigabit per second, but whatever he asks for as far as that, he's going to get it. There we go. Whoop. Okay. So, what happens? How does jitter happen out of this? Jitter happens, imagine user 2 is using the app and pulling data at, I don't know, 0.5 gigabits per second. And everything's fine, right? User 2 is the only one there. There's plenty of capacity in the system to do 0.5 gigabit per second. There's no problem. User 2 is like, la, 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 life is great, okay? Then, user 1 shows up and requests 0.8 gigabits per second for a few seconds. Well, what's going to happen? At that point, right, user 2's effective connection speed is going to drop from 0.5 to 0.2. Suddenly, boom, there's a lot of extra latency, right? Suddenly, he's a lot slower. Then, user 1 asks for a full gigabit per second, right? At which point, user 2 gets nothing. Okay, so again, if user 1 says, oh, sorry, I need all of it for now, then that's really going to slow down user 2's connection speed. And when user 1 goes away afterward, then user 2 goes back to normal. Okay, that's how jitter can happen. One of the ways. is if there are other users with higher priority claims. Yes.
Is that like choppiness in the stream?
That could be part of it, yeah. Yeah. Okay, so that's essentially, latency is the variability in, latency is just the delay, and jitter is the variability in delay. And that's one of the ways that it can happen. Okay. Last, packet loss. So packet loss is a really bad one where some packets don't arrive at all, okay? Some packets may be backlogged, timeout, and the sender may or may not ever resend them. Even if the sender does try to resend them, they're going to give up after a while. They might eventually be permanently lost. So, simple example here. Imagine if user 1 and user 2 are both requesting data from source 1, okay? So, depending on what's going on, how the transmissions are going, okay, there could be like a whole set of packets here between source 1 and the switch is processing them as they come along, and then user 2 gets them. Then, user 1 shows up and says, hey, I got to do this, and everybody out of my way. So, all these packets from user 2, they could sit here in switch memory for a while. But, eventually, they're going to time out, because there's going to be some delay, right? If you can't send them within, say, 5 or 10 seconds, then the switch might say, nope, this packet timed out, I'm not going to send it anymore. And it might get dropped that way. It might take longer, but that's the idea, right? Essentially, if there's a backlog of transmissions waiting to happen, but they're low priority, yeah, they're probably eventually going to get dropped. Another possibility, imagine this. Imagine if user 1 is requesting a full gigabit of data from 2 different sources, requesting it from source 1 and source 2 as going through this same switch. Well, that's going to be a stream of 2 gigabits per second coming into the switch, but the switch can only process 1 gigabit going out, right? So unless you have some kind of synchronization built in, what can happen, the switch memory is going to be able to build up stuff for a while. Probably it has a few gigs of memory sitting there, but at some point, the switch memory is going to be overloaded because it can only send out 1 gigabit per second through that line to user 1. So the packets are going to build up. Eventually, when all the switch memory is full, a new packet going in is either going to get discarded right away. The switch will say, sorry, we don't have memory. Or in order to store that new one, it has to kick out an older one. Either way, a packet gets dropped. Okay, one more slide, then we're done. Buffering, okay? So, to help smooth out these kind of problems with latency and jitter, video streaming applications use buffering. Buffering is fundamentally loading some extra data, so even if there are network troubles, you can keep watching the video because that chunk of data is there locally stored on your machine. So if we go to Coraline here, okay, now we have a good buffer. You can play this and we can see that they're going to sew the buttons on her eyes. So that's what you get. Anyway, so here's the point. Now that we're almost done, there we go. I think we have everything now. There we go, last bit, okay? At this point, you can see the gray bars all the way across. At this point, even if I totally lost my network connection, right, I could turn it off here. Let's go ahead and do it. And shit. I could do it. I could disconnect. I say I'm done. But I can still play the video because I have it all locally stored on my machine, right? That's what buffering is. Okay. So, let's pause that. Okay. Okay, last minute. So, in essence, with buffering, the application builds up a reserve of data, typically several seconds or a couple minutes. The basic trade-off is if you have a longer buffer, more reliable operation. If something goes wrong with the network, you keep playing the video. If you have a shorter buffer, though, you can start playing the video right away. Sometimes, you know, it takes a while for the video to start because it wants to load that full chunk of data. And if you don't have a great connection, that could take a while. So, fundamentally, buffering addresses these 3 streaming problems. If there's a lot of latency, well, guess what? You're good for like the next 30 seconds to a minute, even if the next packet coming in is slow. Same way with jitter. Jitter is just basically an extreme case of latency, right? So if you have enough buffering, you can handle the worst case where one packet or a series of packets takes a really long time to get to you. even with lost packets, even if there are some packets that get dropped, if your buffer is long enough, it might be still, the video might be able to catch them when they get resent, and you'll never know there was a problem. That's what buffering is. All right, come on back Wednesday. We'll have an exam. It'll be